Scientists pointed 42 radio dishes at a visitor from another star system and listened for 7 hours straight, sifting through nearly 74 million signals to answer one question: is anyone out there? The answer wasn't what some had hoped for, but what they learned about our galaxy, our technology, and the nature of interstellar objects may be even more remarkable than finding a message would have been. On July 1, 2025, an automated survey telescope in the Chilean desert flagged something unusual. The Atlas facility in Rio Hurtado, a NASA-funded system designed to spot objects that might threaten Earth, had detected a faint smudge of light moving against the background stars. Within hours, astronomers ran the numbers on its trajectory and realized something extraordinary. This object wasn't bound by the sun's gravity. It wasn't from our solar system at all. It was the third confirmed interstellar visitor ever recorded, and it would soon be designated 3I Atlas. To put that in perspective, humanity had never detected an interstellar object until 2017, when the strange, cigar-shaped one-eye Oumuamua tumbled through our inner solar system and sparked a global debate about whether it might be an alien probe. 2 years later, 2I Borisov arrived looking much more like a conventional comet, putting some of that speculation to rest. And now, 6 years after Borisov, here was a third visitor, unlike either of its predecessors. When 3I Atlas was discovered, it was hurtling through space at roughly 137,000 miles per hour. As the sun's gravity took hold, that speed climbed to about 153,000 miles per hour at its closest solar approach. Its orbital eccentricity, a measure of how much an orbit deviates from a circle, came in at 6.145. Anything above 1.0 means an object isn't gravitationally bound to our sun. Oumuamua had an eccentricity of 1.2. Borisov came in at 3.358. At 6.145, the orbit of 3I Atlas is by far the most extreme of any object ever recorded in our solar system. But what made this object truly fascinating wasn't just its speed or its trajectory. It was where it came from and how old it might be. An analysis of 3I Atlas's pre-encounter path through the Milky Way revealed something that stunned researchers. This comet didn't originate from the galactic thin disk, the relatively young, flat band of stars where our sun resides. Instead, evidence pointed to the galactic thick disk, a region populated by stars that formed during a period astronomers call cosmic noon, an era of intense star formation that peaked roughly 9 to 13 billion years ago. One study estimated with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old. Our solar system is 4.6 billion years old. This chunk of ice and rock may have been drifting between the stars since before our sun even existed. It's a frozen specimen of the early Milky Way, delivered to our doorstep by approximately 7 billion years of interstellar drift. There's some scientific debate here, worth acknowledging. One analysis using data from the Gaia Space Observatory found a 96.59% probability that 3I Atlas originated from the thin disk instead. Different methodologies, different datasets, different conclusions. But even the more conservative age estimates place this object as the oldest of the 3 interstellar visitors we've detected. So when an ancient wanderer from another star system shows up in your cosmic backyard, what do? If you're the SETI Institute, you drop everything and listen. Less than 24 hours after 3I Atlas was announced, the Allen Telescope Array was already pointed at it. The ATA sits at Hat Creek Radio Observatory in Northern California, a cluster of 42 dish antennas, each 6.1 meters across, spread across a volcanic plateau. It was designed from the start as a dedicated instrument for the search for extraterrestrial intelligence. The dishes are equipped with cryogenically cooled feeds, chilled to approximately 70 Kelvin, or about -334 degrees Fahrenheit, which reduces electronic noise and allows the system to detect incredibly faint signals. Each dish is fully steerable, and together they can scan frequencies from 1 to 11 gigahertz. The response time alone was remarkable. The SETI Institute's team, led by researcher Sophia Sheikh, mobilized within a day of the discovery announcement. Within a week, the ATA had already amassed over 21 terabytes of raw data, the equivalent of thousands of hours of high-resolution video. The observing campaign ultimately covered 5 sessions totaling 7.25 hours on target. The team swept through 3 chunks of spectrum, low, mid, and high, spanning from 1000 to 9064 megahertz. That's a massive swath of the radio spectrum. And here's why it matters. Narrowband radio signals, those confined to a very tight range of frequencies, are not produced by any known natural process. Stars don't make them. Pulsars don't make them. Gas clouds don't make them. The only things that produce narrowband signals are technologies, transmitters, communication systems, radar. If an interstellar object were carrying or broadcasting any kind of radio technology, even something as simple as a beacon, that's exactly the kind of signal it would produce. The ATA can record and search billions of frequency channels simultaneously, which makes it uniquely suited for this kind of work. The initial analysis identified 73,974,799 narrowband hits. Nearly 74 million individual signals flagged as potential candidates. That number might sound encouraging, until you remember that we live on a planet absolutely saturated with radio frequency interference. Cell towers, Wi-Fi routers, satellites, military communications, weather radar, aircraft transponders. The electromagnetic environment around Earth is staggeringly noisy, and the vast majority of those 74 million signals were immediately identifiable as terrestrial in origin. The filtering process was methodical. The team applied algorithms designed to separate signals coming from the direction of 3I Atlas from everything else. They looked for signals that drifted in frequency at a rate consistent with the object's movement relative to Earth, a telltale sign that a signal is genuinely coming from something moving through space rather than sitting on the ground. They cross-referenced against known sources of interference and eliminated satellites, aircraft, and ground-based transmitters. After all of that filtering, 211 signals survived, 211 out of nearly 74 million. These were signals that matched the expected characteristics closely enough to warrant human inspection, and each one was visually examined in the time-frequency domain, essentially looking at how a signal's frequency changed over time to see if it behaved like something genuinely coming from the comet's direction. Every single one traced back to technology on the surface of Earth or our own orbiting satellites. 0 candidates survived. The SETI Institute wasn't the only team listening, though. In December 2025, as 3I Atlas approached its closest distance to Earth, a separate team from the Breakthrough Listen initiative turned the Green Bank telescope toward the interstellar visitor. The Green Bank telescope is a monster. Located in the quiet zone of West Virginia, where radio transmissions are heavily restricted, it's the largest fully steerable single-dish radio telescope in the world, with a collecting area spanning 100 meters across. If the ATA is a net cast wide across the radio spectrum, the Green Bank telescope is a spear, offering extraordinary sensitivity in a narrower field. The timing was deliberate. On December 18, 2025, less than 24 hours before 3I Atlas reached its closest approach to Earth at 1.7 astronomical units, roughly 167 million miles, the Green Bank team conducted 5 hours of observations. They used a dual-beam technique, pointing one beam directly at 3I Atlas and a second beam at a nearby patch of empty sky. Any real signal from the comet should appear in the first beam but not the second. Terrestrial interference would show up in both. The sensitivity was extraordinary. At closest approach, the Green Bank telescope could detect transmitters with an effective isotropic radiated power of approximately 0.1 watts, 100 milliwatts, the power of a dim light bulb from 167 million miles away. They found nothing. To be precise, they reported a non-detection of candidate signals down to the 100 milliwatt level. Combined with the ATA results, the SETI Institute ruled out signals stronger than about 10 to the negative 110 watts across the detected frequencies. That's approximately the power of a household appliance. If 3i Atlas had been carrying a transmitter putting out as much energy as a coffee maker, we would have detected it. Some people hear "we found nothing" and assume the whole exercise was pointless. In science, though, a null result is still a result, and this one is particularly informative. It sets real, quantitative constraints. Before these observations, we had no data on whether 3i Atlas was emitting radio signals. Now we know, with high confidence, that it wasn't emitting anything above a very low threshold across a wide range of frequencies. That's a data point, and it goes into the ledger. It was also a live test of SETI's rapid response capability. The ability to pivot the Allen telescope array onto a new target within 24 hours of its discovery, collect over 21 terabytes of data, and systematically process 74 million signal candidates is a demonstration that if something genuinely anomalous does pass through our solar system, we have the infrastructure and protocols to respond. And the study of 3i Atlas itself, independent of any SETI considerations, produced genuinely stunning science. The James Webb Space Telescope first observed 3i Atlas on August 6, 2025, using its NIR-SPEC instrument, and what it found was striking. The comet's nucleus was pumping out 129 kilograms of carbon dioxide per second. That's 284 pounds of CO2 every second, erupting from the surface as the sun's heat penetrated its ancient ices. It was also emitting 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, and smaller quantities of carbonyl sulfide. The ratio of CO2 to water in the coma was 7.6 to 1, among the highest ever observed in any comet, sitting 4.5 standard deviations above the typical trend for long-period and Jupiter family comets in our own solar system. This told astronomers something crucial. 3i Atlas formed far from its parent star, out beyond the CO2 frost line, where temperatures were cold enough for carbon dioxide to freeze solid. It spent most of its existence in the deep cold of interstellar space, preserving those primordial ices in near-perfect frozen storage for billions of years. The Hubble Space Telescope contributed its own observations, first imaging 3i Atlas on July 21, 2025, and constraining the nucleus diameter to somewhere between about 1,400 feet and 3.5 miles. The uncertainty reflects how difficult it is to measure a tiny, fast-moving, gas-shrouded object at interplanetary distances. And then, in June 2026, came perhaps the most extraordinary finding of all. A study published in Nature reported that Josthour had detected an isotopic composition in 3i Atlas, unlike any known solar system comet. Extreme enrichments in heavy hydrogen and unusual carbon isotope ratios led researchers to conclude that this object likely formed in a cold, metal-poor environment during an early phase of Milky Way evolution, potentially 10 to 12 billion years ago. This comet isn't just from another star system, it's from another era of galactic history entirely. As Sophia Sheikh, the lead author of the SETI study, put it, eventually, our own Voyager spacecraft will be extraterrestrial artifacts in other stellar systems. It's a humbling thought. Right now, Voyager 1 and Voyager 2 are drifting through interstellar space, carrying golden records and the fading signatures of human technology. In a few billion years, they might drift past another star, and if an alien civilization spotted one and turned their equivalent of a radio telescope toward it, they would hear nothing. The RTGs will have long since died. The transmitters will be silent. It would look, for all intents and purposes, exactly like a natural object. That's the deeper question Sheikh and her co-author Valeria Garcia Lopez were really getting at. We need to understand what natural interstellar objects look like so that when something genuinely anomalous does show up, we can recognize it. 3I Atlas behaves exactly like a natural comet. Its outgassing profile, its spectral characteristics, its trajectory, all consistent with a chunk of primordial ice ejected from a distant planetary system billions of years ago. That's valuable because it establishes the baseline. The diversity of the three interstellar objects we've now observed is itself scientifically significant. Oumuamua was asteroid-like, with no visible coma and a shape that defied easy classification. Borisov was a textbook comet, and 3I Atlas is a CO2-dominated ancient wanderer from the thick disk. This variety suggests that interstellar objects are being ejected from planetary systems throughout the galaxy's history, not just from young, recently formed ones. As Garcia Lopez noted, the results from 3I Atlas show how realistic it is to detect a signal with the technology we have today. That is why it is important to keep searching for technosignatures, even from objects we might not expect to have signals. 3I Atlas has now passed its closest approach and is heading back out into interstellar space. It will never return to our solar system. It spent perhaps 7 billion years wandering the void between stars, briefly swung through our neighborhood, allowed us to study it with the most powerful telescopes humanity has ever built, and is now disappearing back into the darkness it came from. We pointed our instruments at it and heard nothing but silence. But that silence told us something. It told us we have the tools to listen, that we can respond within hours to an unexpected visitor, and that at least this particular ancient traveler from the early Milky Way was exactly what it appeared to be, a frozen relic of a long-dead planetary system, carrying in its ices the chemical fingerprints of a galaxy that existed before our sun was born. The search continues. With each interstellar object that passes through, we get a little better at knowing what to listen for, and a little more certain that when something truly anomalous does arrive, we won't miss it.